16, now we get into applying the fundamental theorem somewhat. All right, so it says find f as a function of x, so capital F as a function of x, then evaluate it at x equals 2, 5, and 8. All right, so what we're going to do is integrate. So 1/4 t to the fourth plus t to the second minus 2t over the interval of 2 to x. All right, so we can make some substitutions now. All right, plug in the x and then plug in the 2 and see where that takes us. And what we'll end up with is a function of x. All right, so 1/4 x to the fourth plus x to the second minus 2x minus 1/4 times 2 to the fourth plus 2 squared minus 2 times 2. Okay, so some nice things happen. I mean, I wouldn't say it's lovely, but it's pretty good. 2 squared minus 2 times 2, that's going to go to 0. And so this expression here, which is now exclusively in terms of x, can be defined as capital F of x, 1/4 x to the fourth plus x to the second minus 2x. Now we have minus, well, 2 to the fourth is 16, a quarter of 16 is 4, so minus 4. All right, so what they're saying for us to do is evaluate it for when x is equal to 2, 5, or 8. All right, so if you wanted to, you could do this a couple of different ways. You could pop it into your calculator and go to the table. But I'm also going to show you very quickly just a quick review of the remainder theorem, just because it's a nice, quick, by hand way of evaluating functions. All right, so the way you would evaluate a function if you're using the remainder theorem would be to list out the coefficients in descending order, just like you would for synthetic division. So a quarter, there's no power of 3, so we put a 0 coefficient there. A 1 for the power of 2, a -2 for the power of 1, and a -4 for the power of 0. And then run through with the 2 using synthetic division. So 1/4 times 2 is 2/4, which is 1/2. Add them up. 1/2 times the 2 is going to give you a 1. Plus the 1 that's already there is going to give you a 2. Times the 2 is going to give you a 4. And then add that to the -2, and you're going to get a 2. Times the 2 that's already there, or the 2 on the outside, is going to give you a 4. Add them up and you get a remainder of 0. And so what that tells you is, based on the remainder theorem, is that f of 2 is equal to 0. All right, so I figured I would just take a second and review that because it's pretty useful. It's quick. When you're substituting in values like a 2, it's, all right, you look at it and say, okay, well, maybe it's not that quick. But it's not bad. For complicated values, it actually goes fairly quickly. All right. Now, if you're using the calculator, and I also like to cover it because it's often a skipped topic in pre-calc, because it's like, oh, when are you ever going to need this? We have calculators. It comes up often enough that it's worth learning. All right. So another way of handling it would be to put your equation in, your function in, and go to the table, second graph, and take a look at the x value of 2, see what that corresponds to in terms of y, which is 0, as we determined already. A 5 gives you 167.25, and an 8 gives you 1068. All right, so f of 5 and f of 8. All right, so you can do it that way too. All right. Now, the next example says integrate to find f of x. All right, so we'll do that. Then differentiate to show that the second fundamental theorem holds. All right, so let's take a look. So first I'm going to rewrite this as going from 4 to x of t to the 1/2 power dt. Increase the exponent by 1, divide by the new exponent. We're looking at t to the 3/2, divide by the new exponent gives you 2/3 over the interval of 4 to x. All right, so what I'm going to do is replace the t first with an x, and then with a 4. All right, so that's one way of representing our capital F of x. Now I'll get the equal sign in there too. Now what this is telling us to do is differentiate it to show the second fundamental theorem holds. All right, so let's take a look. So let's find the first derivative of this function. Multiply power by coefficient. You're going to get x, and reduce the exponent by 1. You get x to the 1/2. Regardless of how complicated that second term is, it's still constant. There's no variable there, so that's going to 0. So this actually gives you just a square root of x. The second fundamental theorem essentially is telling us, and if you go back to the previous page, you could see this in the formula. It's telling us that all you really have to do, if the upper bound is an x, is replace the variable t with an x if you are differentiating the antiderivative. And that's really it. All right? So when we're looking at the next example, it's really going to be as simple as saying secant cubed of x. It only starts getting a little more complicated when you incorporate a variable bound that's not as simple as just an x. All right, so that's when the chain rule comes into play. All right, so what we do here is essentially, we apply the chain rule. So what we do is we multiply by the derivative of the upper bound, and that's the only difference. So when I find the derivative here, so f prime of x, I'm going to replace the variable t with the upper bound itself. So 1 over x squared cubed, and then I'm going to multiply by the derivative of the exponent, I'm thinking exponentials. I'm going to multiply by the derivative of the upper bound of integration, which is going to be 2x. So we're looking at 2x over x to the 6th, simplify 2 over x to the 5th. F prime of x, cosine of x cubed multiplied by 3x squared. All right. The last example here is the one that makes things a little trickier, because it's 2 variable bounds, and it's like, okay, well, do I substitute in the x or the x squared or both, or do I subtract them, or do I have to do it the long way? You get creative. All right, the creativity comes into play if you know your properties of definite integrals. All right, one of those properties allows you to break up an integral based off of some constant between the lower and upper bound. So what I'm going to do is I'm going to rewrite f of x as the antiderivative going from x to some unknown bound, some unknown but constant bound a of cosine of t dt And then I'm going to add that to the derivative, the antiderivative, going from a the rest of the way to x cubed, also of cosine t dt. All right, since I'm looking for the derivative and I'm involving a sum, I can take the derivative of each piece separately. All right. We also learned that you can swap the bounds of integration as long as you negate the integral. All right, so if I want, the second integral is fine, but if I want the first one to be in the proper form, I can swap the bounds as long as I pop a negative sign in front. So now if I want to differentiate, all I have to do, well, aside from not forgetting that I have a negative there, is apply the second fundamental theorem, replace the t with an x here, so cosine of x, plus, and then replace the t here with an x cubed, so plus cosine of x cubed, but then multiply this one by 3x squared, which is the derivative of the upper bound of integration. And that's it.